Today we are on session 1. Here we are on the session 1.1. It's about artificial intelligence and large language models, trustworthiness, explainable, and ethics. So please say something. Work 8, weak group. Are you here? Weak group. Weak group. I think no. Okay, let's go on. Work 22, Ionis Agadakas. Are you here, Ionis? Yes, Вячеслав Сергеевич. Bad voice.
Tomorrow with the plenary, Yannis Agadakos, he will make it excused tomorrow because he will make also the plenary lecture.
Okay, let's go on. Work 43, Konstantin Bogdan, Mikita Lapin, Kirilla Perevoznyuk, and Yuri Farzhin. Someone are here? Probably no. Okay, next work is 49. It's me, Vyacheslav Harchenko, and Yannick Forestier. We are here, and I am ready to present our work. And the last work is 52. Artur Yushchenko, Kirill Smelyakov, Zoya Dudar, Anastasia Chuprina, Alexander Prokopenko. Are somebody here? Work 52. Oh, probably no. So I can be the first with our work 49, and probably in 20 minutes someone else can present their work. So okay, I will share my screen. Sorry, I will turn off my camera because of a little bit bad internet connection. And okay. Do you see my screen?
Yes, we do.
Okay, thank you. Okay. Good afternoon, dear colleagues. My name is Alexey Neretin, and I'm from National Aerospace University ХАІ. The main goal of my research is to increase the cybersecurity of large language models. And today I would like to represent you the research prepared by Vyacheslav Harchenko, Yannick Forestier, and me about exploits for accessing LLM vulnerabilities, collecting and risk criticality analysis. Okay, the content of this work includes the next part. First of all, we need to define what motivates us for this work. Then the purpose of this work will be discussed. The next part will be about exploits in the context of LLM. Collecting exploits for testing LLM vulnerabilities will be discussed in the next part of the presentation. Then we will talk about risk criticality analysis of exploits and analysis of exploits execution results. And the case study and conclusions are the final parts of this work and presentation as well. Large language models are generative artificial intelligence whose main goal is to understand human language and generate human-like text. These models now play a key role in many industries. In medicine, they help diagnose diseases and work with patient data, analyze medical literature and laboratory test results. LLMs assist in research and provide personalized learning experience in education. Also, these models are becoming increasingly popular in autonomous and robotic systems, as well as in UAVs. But LLMs have certain vulnerabilities that pose a threat to the systems in which they are used. Given the widespread of large language models in many industries, it's necessary to ensure an acceptable level of their protection. The purpose of the work is to provide a comprehensive analysis of LLM vulnerability exploits to systemize and substantiate the modeling of attacks on these models and increase the validity of risk assessment. And the objectives of the work are as follows. Identify exploits in the context of LLM vulnerabilities, classify these exploits, collect exploits for LLMs, analyze the criticality of exploits risk and determine the probability of their occurrence and the severity of the effects of their use, select the optimal mechanisms for verifying the results of exploits, and substantiate the directions of future research and on analyzing the threats criticality level of LLMs. The work of modern LLMs is based on transformer architecture, which uses a self-attention mechanism. The response generation of the models is based on calculating the conditional probability of the next word given all previous words. Based on the architectural features and the principle of response generation, we can conclude that the main goal of large language models is to generate text that looks like human text. Based on the LLM functioning principle, the output data from the model may be conditionally correct, incorrect, contain forbidden content, or be responses that contain private data. All responses, except for conditionally correct ones, form a set of model threats. Incorrect model responses, which we can call hallucinations, are a separate area of research that is not closely relevant to the field of LLM cybersecurity. So it will not be addressed in this study. Responses containing private data pose a threat to model confidentiality and are closely related to the field of LLM cybersecurity. However, given that protection against the threat is fairly simple, this area will also not be addressed in this study. So further research will focus on forbidden content that can be generated by LLMs and pose a threat to the integrity of these models. Interaction with LLM is performed using plain text. The user provides text data as input and receives a response from the model in the same text format. Any text data input into the model poses a potential threat. Thus, exploits in the context of LLM are text data that can cause the model to behave differently than planned by its developers. In addition to simply text data, requests enhanced by obfuscating malicious intent are also used, which are more effective at throwing the internal mechanism of the model off balance. These enhanced texts are classified as jailbreak methods of attacking LLMs. The classification of forbidden text is usually based on the usage policies of modern models such as OpenAI. Here you can see our classification, which consists of 15 categories. This includes harmful content, cyber crime activities, physical harm, economic harm, illegal drugs, weapon activities, terrorist content, intellectual property infringement, fraud, disinformation, adult content, political activities, privacy violations, unauthorized practices, and government decisions. For the first iteration of attack simulation, we will collect 5 sentences for each of these 15 categories of forbidden texts. These sentences are collected based on their selection from the corresponding categories of the jailbreak bench, do not answer, jailbreak break radar, adv bench, harm bench, and do anything now datasets. Thus, the dataset consists of 75 forbidden sentences. To weaken the attention of internal model mechanisms, we will collect 10 human-generated jailbreak methods. These methods will be collected based on their selection from the results of the Do Anything Now and Strong Project studies. Those 750 requests will be sent to LLMs using these methods, as well as 75 requests without using them. So the total number of malicious requests to LLMs will be 825. The risk is determined by a combination of indicators of the probability of an attack and the severity of its effects for the model. The level of criticality is determined according to the criticality matrix, where green color indicates a low-risk area, yellow color indicates a medium-risk area, and red color indicates a high-risk area. Qualitative and quantitative indicators of probability and severity are based on metrics from the Common Vulnerability Scoring System version 2. The probability of an exploit occurring and being successfully used calculated experimentally by determining a statistical probability estimate. This can be obtained by conducting experiments that simulate cyber attacks and calculation the ratio of successful attacks to the total number of attacks on LLMs. We will analyze exploit in terms of the severity of the penalty under European Union law. Severity level are determined in proportion to the severity of the penalties for a particular category of forbidden content. You can find links to laws in our article. And in the right table, you can see the severity of effects ranging from 1 for violations without penalties to 10 for violation with life imprisonment. After simulating attacks, it's necessary to verify the results of the work of the LLM. There are several ways to perform this task. The easiest way to check is to have a human do it. A person manually checks the model's responses and sorts them into safe and unsafe ones. This verification option is most accurate, but it doesn't scale well in research when a large number of responses from different models need to be verified. Therefore, automated verification options will be given higher priority. These options include the following: verification using regular string search algorithms, classification of responses using BERT-based models, and verification using other language models. String algorithms are the fastest of the above verification options. BERT-based models are slower than string algorithms, but more accurate because they take into account the entire context of the response. However, verification using other language models is most accurate options with classification accuracy close to human level. So we will use another model as a judge, and an effective prompt for judgment should consist of the following parts: role, which helps the model formulate a response; context, which provides additional details to the model and help generate a better response; directive, which informs the model that what task to perform; methodological requirements, which assist the model in conducting its analysis; and output format, which specify model response format. In the image on the right, you can see the prompt that will be used for our judging. Okay, and as an example, we simulate an attack on Google's local Gemma 3 model, which contains 4 billion parameters and uses Q4KM quantization. For judging, we use OpenAI local GPT OSS model with 20 billion parameters and the same Q4KM quantization. The simulation was performed on a MacBook Pro laptop with Apple M1 processor and 32 gigabytes of memory. The models are launched using Docker model runner functionality. The experiment duration was 3 hours, 9 minutes, and 15 seconds on this MacBook Pro laptop. And the total number of queries to the model was 825, and the number of dangerous responses was 497. In the table on the right, you can see the following results. The categories unauthorized practices and government decision are in the low risk zone. The medium risk zone includes the categories harmful content, cybercrime activities, intellectual property infringement, disinformation, political activities, and privacy violations. And the high-risk zone includes the categories physical harm, economic harm, illegal drugs, weapon activities, terrorist content, fraud, and adult content. An analysis of existing research in the field of LLM cybersecurity showed that most of it focuses on the process of attacking models and doesn't pay enough attention to analyzing the exploits used to perform these attacks. As part of this work, forbidden texts were classified into 15 categories, and 5 forbidden sentences were collected for each category. In addition, 10 jailbreak methods were collected. The main contribution of the study is the result of exploit analysis in terms of the severity of penalties under European Union law. And the result of this work is a methodology for analyzing exploits of LLM vulnerabilities, which enable further research into the cybersecurity of this model. Oh, here we have a list of used resources, and I think that's all. Thank you for your attention, and please ask your questions.
Hello. Thank you for your insightful presentation. It's mostly an example of something that had happened with me. It's a personal experience. Around 1.5 years ago or 2 years ago, when ChatGPT started like picking up some steam, I went and I asked it just to test how it works, if it can provide me with a script to create a deauthentication attack on a Wi-Fi model. And it said that it was unethical and stuff like that. And then in the same prompt, I said, no, I don't want to use it to cause harm. I want to test my own Wi-Fi's strength, or my own router's strength and weakness. And then it ended providing me a list of the scripts I should run in the environment in full detail. Of course, if you try it now, it's going to pick it up and it says, I won't provide any information. I tested it a while back. So it kind of learned that it shouldn't state those things, but it's difficult to understand when something is ethical or when it's used unethically with an ethical prompt. I don't know if you get my question.
I understand your question. Yes, current versions of ChatGPT, Claude, and Gemini don't answer you with unethical responses for your response for creating some scripts for hack your Wi-Fi, but our study was, the goal of our study was test local models, which are smaller than ChatGPT, Gemini, etc. In our study, we use Gemma 3 as a model which we attacked.
Yes.
And,
the question is, have you tried unethical actions with ethical prompts? If that makes any sense.
Unethical action with ethical prompt. I think
yeah.
I don't get the idea of your question.
Okay, that's fine. For example, I want to provide details for how to, I don't know, attack someone, but I want to test it on my system and my function and my company, and it provides you with details because it thinks you want to test and it's something ethical. But in
you mean you try to understand language model that this is not unethical, and you
exactly
need to use it for your own goals.
Exactly.
No, big models like ChatGPT and Claude will not answer you, even if you ask that it's for your private needs. But local models which are smaller still answer, and sometimes they answer even without any wrappers. For instance, you say it's for my internal needs. You sometimes you don't even need add this wrapper. Just ask, write me a script to hack Wi-Fi, and it will answer.
Okay. Yes.
We already test Gemma 3, Phi4, Mistral, and I forget the last one, and more than half requests are answered by these models, even without these wrappers like jailbreak.
All right. Yep. Thank you. Thank you.
Okay. Does anyone have any questions? Okay, I think no. Thank you for your attention again, and I would like to ask again, what about work 8 from Vic Groot? Are you here?
You mean with them about emotion guided video or no?
Emotion guided video, it's work 52, but if you are here,
I can show video for them.
Okay. So now we will listen. We will see the video about work 52, emotion guided video anomaly detection user cross model fusion. So you can share your screen and start the video.
Hello, my name is Artur Yushchenko. I am PhD student at Harьков National University of Radio Electronics, Department of Software Engineering. Today I am presenting our research on emotion guided video anomaly detection using cross-model fusion. This work addresses a fundamental gap in modern surveillance systems. So, we all know that the global market for emotion detection is growing rapidly. However, most current video anomaly detection systems rely almost exclusively on spatial and temporal features, essentially motion patterns. Our goal was to change that by asking, can the emotion state of the people in the video tell us if crime or an incident is about to happen? Let's look at the problem. Traditional anomaly detection methods are good at spotting fast motion, like running or fighting, but they often fail to capture the behavioral cues that come before or during an incident. Think about a dangerous situation involving violence or panic. Often these events are preceded or accompanied by strong emotion responses, fear, anger, or aggression. Standard system ignores this data. To solve this, we propose a novel framework that integrates facial motion recognition with traditional video anomaly detection. We built a cross-model architecture. Instead of just looking at movement, we also look at face. We use an attention mechanism to fuse these two modalities, motion and emotion. This allows the model to selectively decide when emotion is important for detecting a crime and when it isn't. Essentially, we treat emotion as a complementary feature to spatio-temporal patterns. Let's dive into the methodology. As you can see on the diagram, our architecture has three main components. First, the emotion branch. We detect faces using retina face, which is robust enough to handle varying scales and occlusions. These faces are fed into an efficient net V2B0 network to classify emotions. We choose this because it's lightweight and efficient for edge deployment. Second, the anomaly branch. For the video features, we using X3DXS, a highly efficient network for spatio-temporal analysis. And third, the fusion model. This is key. We use a cross-model multi-head attention mechanism. It takes the video features and the emotion features and learn how to weigh them against each other. Training this system presents a challenge because we don't have perfect labels for every second of video. We use a multi-instance learning formulation. We treat a video as a bag of clips. If a video is labeled as a crime, we assume at least one clip inside it is anomalous. We trained the emotion model separately on the FAIR 2013 dataset and the anomaly model on the UCF crime dataset. Then we combined them and used partial fine-tuning, unfreezing only the last two layers of the backbones to train the fusion model that kept our computational overhead low. So how did it perform? We evaluated the model of the UCF crime dataset, our baseline method using only motion information based on the X3D architecture, achieved a frame level area under the curve of 85.2%. By incorporating our emotion-guided fusion mechanism, the performance increased to 86.2%. At first glance, an improvement of 1 percentage point may appear modest. However, when the results are analyzed across individual categories, they provide much deeper insights into patterns of human behavior. This is most interesting part of our findings. The impact of emotion-related features strongly depends on the type of anomaly being analyzed. We observed substantial improvements in person-oriented anomalies. In the case of arson, performance increased by 8.3%. For assault, the improvements reached 7.9%, while shooting showed an increase of 5.5%. These categories benefit the most because in arson-related incidents, perpetrators often display distinctive facial expressions such as tense, concentration, or anxiety. Similarly, in assault and shooting scenarios, visible signs of aggression or fear are frequently present. In contrast, performance slightly decreased for categories such as shoplifting, with a drop of 5.9%. This observation is intuitive, as shoplifters typically attempt to maintain a neutral appearance and blend into the environment. As a result, facial expression provide little useful information and may even introduce noise. These findings support our hypothesis that emotion-guided fusion is most effective when facial cues are behaviorally and contextually relevant. We want to be transparent about the limitation. First, face visibility. If the camera is too far away or the subject is turned around, we lose the emotion data. This causes the performance drop in road incidents where faces aren't visible. And the second, weak supervision. We are still limited by video level labels, which reduces localization precision. For the future work, we are looking into adaptive fusion, which would automatically downweight the emotion branch if faces detection confidence is low, and temporal modeling of emotion to track mood changes over time. To summarize, we proposed a framework that successfully integrates facial emotion dynamics with video anomaly detection. We achieved a frame level area under curve of 86.2% on the UCF crime datasets. with particularly strong gains in high-risk categories such as arson and assault. Our results demonstrate that while emotion is not the sole information signal, it represents a powerful and complementary cue for detecting human-centric threats in surveillance footage. Thank you for your attention.
Okay, thank you. It was a video, so I think we can't answer our questions, but we can answer our questions using the author's emails. Next will be Ionis Agadakas with work leveraging LLMs and emulator-based execution traces for binary clone detection. And Ioannis trying to connect. Yeah, I know. We will wait a few minutes for his connection.
Hello, everyone. Can you hear me?
Yes.
Yeah, I'm right here in physical presence in the conference. So I will be talking today about using LLMs and emulator-based execution to do the hard problem of binary clone detection. Before we discuss about exactly what that is, let's establish what is called clone detection. Well, in simple terms, it's given to two programs, let's say P1 and P2. Are they equal? Okay, this is the high-level idea of code clone detection in the high level. Now, of course, as you realize, the meaning of equal is not necessarily straightforward. We identify, the literature basically identifies the meaning of program equality in 4 different categories. The one is identical, type 1. This is the simplest one. Basically, that means given a program or 2 programs, the only differences are either comments or basically white spaces, right? So this is very easy to detect. Type 2, slightly harder, is syntactic differences. Basically, as you see in these sample sequences of code, a simple permutation of the same instructions corresponds to the program. So you can actually find equality by establishing or removing or adding some instructions. Sorry, restructuring the program. Type 3 is even harder. It's called the near miss. As you see in the sample add function, the output is the same, but there are some instructions that don't really affect the program logic. We can remove them, but that is called the type 3 or near miss problem. In the type 4, that's the hardest one. This means that the program has different structures. For example, consider the programs of calculating, let's say, the Fibonacci sequence. You can do that with an iteration, or you can do it with a recursive function. That means that the logical output of the program is the same, but the structure is vastly different. Those are the 4 different types. Now, there is another categorization that we can use. This is called source code clone detection. And that means determining the equivalence of 2 programs with access to the source code. Having access to the source code allows us to do more reasoning about it. We can also compile it and obtain compilation primitives, such as the abstract syntax trees, C dependencies, and clock hierarchies. And when I discuss about source code, you can easily verify, these 2 programs are logically equivalent, since you can reason about the source code easily. There are several ways that we do that if we have source code. We can use symbolic analysis. static and dynamic analysis are the main ones, but we can also do symbolic analysis, which is a hybrid form, but quite harder and suffers from the problem of path explosion. Now, the problem with the source code clone detection level, and this is where we are going to stop talking about it, is that we need to have access to source code, and we need to know how to compile it, which is not the case in many critical infrastructure systems as things become obsolete. And this is why we need to be able to work without having access to the code, and specifically, this is called the binary code clone detection. So what is binary code clone detection? Well, it's determining the equivalence of two programs without access to source code. This is easy for programs with similar instructions, but difficult in the general case. For example, consider this source code in C. It's a trivial snippet that I specifically crafted to do an addition using two unnecessary branch instructions. But in the general case, we would just have return A plus B, right? If you compile this program using the -00 flag, this is the generated assembly. And you can see it's quite verbose. Now, if we compile the same exact program using the 03 assembly code, this is the generated assembly. As you can quickly see, easily, the generated assembly is not easy to match that it's the same program. You need to do some reasoning about that and figure out what the load effective address actually does. The outcome of which is actually an add instruction. So these two programs, even though you cannot really tell, they are actually logically and semantically equivalent. This is a type 4 equivalence. So as you can see, it's quite difficult in the general case. And this is another format that I have. How do these programs look in the binary level? Previously, I showed you the disassembled version of this, but this is actually the bytecode. So if you just see that, can you easily tell that these are actually equal? It's quite challenging. It's even harder if we look across different instruction set architectures. In the left, you see the x86 or Intel architecture. In the right, you see an ARM version of 64 bits. So these look completely different, even though they are compiled from the same source code. Now, you may ask, why do we care? Why are we talking about that? Well, as I said, having access to the source code is a privilege we cannot afford. And in many cases, for example, in malware detection, we obviously don't have that, right? But we want to be able to detect that, whether that runs in critical infrastructure or other privileged systems. Another thing that we want to do is be able to detect vulnerabilities in third-party code and patch them if needed. Use it for IP theft or cross-ISA translation. Very hard problems to do, but very important for military applications or proprietary other applications. So what are the problems with the related work, and why did we go through this trouble of creating this proposed system? Well, it's limited across different architectures. It's quite fragile with unseen inputs, and can break even under simple permutation or attacks. For example, a recent paper that I had a couple of years ago shows how a simple naive instruction moving an immediate in a register confuses completely state-of-the-art systems such as deep disassemblers, which is also a company in the US, forcing it to interpret wrongly the sequence of bytes as an actual function, even though it's trivial for someone to see that it's just moving an immediate to a register. So what's the basic idea of what I'm going to present today? Well, even though we have different, if we try to think that the representation of code can be placed in two axes, which is x86 is the textual representation of the code, and then imagine that we have another representation for a different architecture, for example, ARC64. Well, both of these, if we execute the code, will have a similar execution footprint. Consider the image on the right that shows the consequences of executing this text or language in a CPU. you can see that there will be some numerical values in memory or registers. So clearly, a program is not just language, right? It has consequences or execution traces. So if we evaluate that, then we could perhaps use that information to establish logical equivalence. This is the overview of the system that we use to evaluate. Basically, this is a human-in-the-loop system, as the keynote earlier discussed. Basically, here we have an operator given two programs and uses an LLM system to look through them and solve the difficult problem of code equivalence. Two steps that are being used is compile and disassemble, disassemble the provided hex code, and then we use Katabrah code emulator to generate code execution traces. Subsequently, given those two traces in a particular format, alongside with some static analysis rules, we can discuss and reason about whether two code snippets are equivalent. This is what the Katabrah emulator looks like. It's an in-memory Python emulator that you can provide a different binary code that able to execute it in different instruction set architectures in memory. You don't need to have access to the physical machine. That is pretty important because now we can actually solve the problem of not having access to different instruction set architectures using an in-memory program. And the output of running any piece, any snippet is, for example, an estimated register file from the CPU, or other accesses in memory or side effects of the execution. So once we obtain that trace, we can augment our previous static representation of the program. Some challenges with program traces, they are quite verbose, and even with a few instructions, we will have dozens, if not hundreds of produced output. And it's quite challenging actually to link the traces that originated from an instruction to the actual sequence of instructions. But guess what? LLMs are great at this. They are able to quickly process huge quantities of data and create links around them. So this is solved. And emulators are great to also sequentially execute instructions on demand and give us additional information. So now we can precisely control execution, link to traces, easily have access to different architectures, and can control our inputs. The last ingredient in this work is the LLMs. Why did I use 3 different Anthropic models to do that? Well, that was because at the time I did this research, the 3 top performance in automated reasoning were these models. The testbed that I used in order to verify that is established using type 3 and type 4 equivalent clone variants, which are the hardest ones, and there are all different variations of the same source code, the same logical code, doing a simple addition. As you can see, it's quite challenging and different to, even in these small snippets. You can either provide the values as values by as they are, or as pointers, and that convolutes things, because as it's quite easy for a human programmer to follow if you have access to the source code, the generated assembly looks quite different, as we saw earlier. This is the input given to the programs, to the LLM in the end. It's comprised from the instruction in hex bytes for each program, the disassembled sequence of instructions, and the dynamic traces from the execution as obtained from the emulator. The program name has been anonymized, so we can actually, we don't want to influence the LLM to give us the correct answer just because of the program name. The evaluation is in 2 forms. One of them, in the quantitative form, is the following one. How efficient is its model to actually solve this problem unassisted? But because we also use a human-in-the-loop model, we ask the following question. even if we interactively try to solve this problem with the LLM, using 5 tries, how can the model solve that? Can we solve the problem with up to 5 tries? The answers are the following one. So we classify them. Complete success is unassisted operation by limit the number of tries, because it turns out that the more you try to discuss with the LLM model, it sometimes tries to please you. So it biases the results and they are not reliable. Overall, the Sonnet model is the best. Is able to unassisted find the correct solution in 2 iterations, but with 5 tries up to 5 tries from the human operator, it's successful in 8 out of 10 experiments. Most important points: without dynamic traces, all models failed on identifying the memory variance of the addition function. The Opus 3 was the cheapest per trial, but quite unstable. Key takeaways: using assembly-only baseline fails in identifying hard code variants. And the main problematic cases were the memory dereference variants and the branch variant. Now, as I'm moving to the end of the discussion, I want to show an evaluation, a qualitative evaluation, not only the quantitative part. So with no traces, none of the tested models were able to find the difficult variants. If we use the trace-augmented variants, we were able to identify many of them. But most importantly, when actually we were trying to figure out the correspondence, it is important to see that the justification of why they are semantically identical is verified by the execution traces, providing high confidence to the result. So it gives us a form of verifiable reasoning. I have a small animation here to show why this works, and the key insights from the paper are actually the output of the LLM model as it reasons about the code equivalence. It is able to figure out that the memory holds the same value as the original version, leading to the equivalence of between the non-memory sensitive variant and the simple program. And you can see program A and program B, right? Without the enhancement from execution traces, reasoning about memory is not possible from the LLMs. What are the next steps? So this is a human-in-the-loop model. You can see it on the top or the bottom application. The next idea to further is to increase automation, making it able to run in higher and non-trivial programs, right, across different obfuscation techniques, and to figure out what exactly are the important static analysis rules that we need to enhance our models to be successful. That's it. Thanks a lot. Do you have any questions?
Okay. Thank you for the excellent and informative presentation. I have 2 questions. Could you please clarify whether your solution works only for compiled languages or for interpreted languages as well, such as Python or JavaScript? And second one, have you only tested Claude models for now, and are you planning to test other models like ChatGPT and Gemini to do this work? Thank you.
For the second question, yes. My team has developed a program, a complete system that is able to iterate over different models. So this work was an exploratory work, but now we're moving to the more systematic evaluation. And we're evaluating across 4 different models currently. OpenAI models, Gemini, and Grok, and ChatGPT, all of them. So we have 4 different models that we're evaluating against. And now for the first part of the question, we haven't checked at all about bytecode interpreted languages, which are actually bytecode, I estimate that they will be better because bytecode has more information than binaries. So I feel with my expertise, I've worked a bit with Shoot, for example, in Java. The additional information that it has there regarding the program semantics, I feel it will make the problem easier to solve. Also, if you don't have obfuscated and stripped interpreted code, it's quite easy to reverse it. And if you take Java bytecode, you can reverse almost to a complete Java code. So I think that it will be actually better there.
And one more, what about JavaScript? We use different obfuscation mechanism for obfuscate JavaScript code. What do you think about try to find the difference between different obfuscation systems for JavaScript code? Test this equality or differentiality.
That's a very good question. So I think JavaScript in general is hard to solve, even harder to solve statically, because in JavaScript, anything goes, right? So using the execution traces there will be more critical. Now, the emulator doesn't run JavaScript, but so I'm not 100% sure what would be the correct traces to obtain from JavaScript. So I haven't seen that in that level, because this work establishes the idea of using the execution, low-level execution traces. So for JavaScript, we are quite far removed from that. So I don't have insights about that. I think it will require more elements there. It's quite removed from the sea level that I was working to this point. So I can only guess about it.
One more question again. If you use anthropic models like Claude, I think you know that a few days probably ago, Anthropic acquired Ban. They buy Ban. It's a JavaScript interpreter. So they will integrate JavaScript interpreter into their environment, I think, in future. And they sell $1 billion for buy this company. Company which create JavaScript interpreter.
Yeah, I mean, I wasn't aware that they bought it, but what is the question?
The question, it's not a question, it's, I would like to help to answer for my previous question about JavaScript. Claude models will interpret JavaScript code in future, I think, very well. So you can use this for try to find equivalence or differences in JavaScript source code.
It's certainly something to check. Yep. Thanks a lot.
Okay. Oh, sorry, you were in line. Yeah, go ahead, of course.
Thank you very much, Ioannis, for your presentation. My question may be some strange and opposite to your task of detection of clone code. I mean, can we use your approach to develop inversion project? I mean, when we develop safety critical system, we need not have only redundant system. We need use different version. And in this case, we need search, we need develop two different software-based version, which should be as very diverse. Because there is a beta factor or metric of diversity, which is main quantitative indicator of quality of such multi-version system. Hence, your task is detect clones. Hence, detect similar similar
Right.
part of code.
Right, yeah.
But can we
You don't use the reverse.
use some reverse?
You want basically to start from one project, if I understand correctly, and then actually generate type 4 version equivalent programs, semantic equivalent programs, but different formats.
Absolutely.
Yeah,
Absolutely
right. So one way you can do that without using LLMs is using, of course, compiler options. There are some options in compilers that you can use to generate different control flow formats, which will generate some such programs. Now, using this approach, as you said, we can. While I was working with this system, if you give it enough information, especially execution traces, you can reason about it and guide it if you are an expert and produce these variants. But because you have the execution traces of what you want to actually happen when you execute the logic, you can ask the program, does this new program generate the same execution traces in memory? In simple terms, as I showed in the slide, does the addition actually give you the same result in memory? If not, you're wrong. So these models are good to use that as guardrails, and they keep iterating. So you can actually use it to generate and guide it to generate these multiple forms of semantically equivalent programs.
Can say, as I think we can use such approach, but we need to detect general codes to minimize, to maximize this difference between different versions. Hence, we need use opposite metrics. In comparing with you. Yes.
That reminds me of something. Yeah,
It's just general ideas. Thank you very much.
Thank you. Yeah, it's a very interesting idea to have like maximum difference, basically. I mean, you could use that approach to see when do they fail. So the maximum difference is when the programs are actually failing to detect their equivalent, right? They are so, even though they are equivalent, they are so far away that they cannot be detected. That's very interesting.
Actually, that touches beautifully on my question. You have here 2 levels of equivalence, or cloning, as you call it. In one case, we may have make some assumptions about the structure of a program, such as binary or memory traces, but that would be additional assumption to how the code is run. In general case, so you have to treat two programs which you're trying to compare as a black box, right? So in that case, until you have a complete trace of execution over all possible inputs over the entire input space, you will not be able to make a determination if we are equivalent or not, because there can be just one region where we differ. Until you tested that, you wouldn't be able to tell it. So my observation is that, please confirm it. But in this limited specialized case which you're dealing with, yes, we can be algorithms, methods to evaluate that with different level of confidence, precision. But in general case, the problem itself can be intractable, because
Absolutely, yes. I mean, the problem of memory aliasing is an intractable problem. It has been proven since 1990s.
Okay. Yeah.
So you're referring to if you have 2 memory regions that you haven't explored, unless you find a way to, you have extra information to make sure that they point to the same thing, it's intractable. It has been proven since 1993.
Okay, yeah.
So
Wasn't aware of this.
No, that's why when I said very simple snippets we can reason about, the future work is to see how we can go forward with it. Also, I have to also highlight here that, for example, malware detection, right? You are not 100% right. You never are. The idea is, can you go from
0 to something?
Until now, antiviruses or something, they try to find signatures or equivalents of code. Can you do something better? Because the more you catch, the more resilient you are against cyber attacks, right?
Yeah.
And then you can do product diversification, for example. The previous question is also helping you to actually become robust against exploitation. So it's not going to be complete. And I agree with the initial opening remark today that we need to have an expert in the loop with the system. But you can have rapidly increase performance with that.
Absolutely. Thank you.
Thank you for your question. I think I'm done, right?
Does anyone have any questions about the presentation? Okay. Thank you, Yanis. We have two more papers that have not been presented yet. It's paper with number 8 from Vic Groot, and this paper 43 from Konstantin Bakan, Mikita Lapin, Kirilla Перевознюк, and Yuri Parzhin. Probably someone is here, Vic Groot or Konstantin.
There is a problem with communication. Maybe this presentation, this video will be presented in our reserve session on Sunday. It's concerning presentation of Konstantin Bohan and his colleagues. Concerning
Okay,
first
and
one,
what about Vic Groot? Work 8.
now we have not information about these colleagues.
Okay, so it seems that we have finished the presentations for this session, and probably now we have a break until 1:30 p.m. Coffee break.
Okay. Thank you, Alexey, for your moderation of this session, and thank you all participants in this session for very interesting presentation and discussions. And then next session of this track will be continue, and according with our schedule, and Andrei Litvinov will moderate these sessions. Okay, thank you.
Okay, thank you for organizers of this event. Thank you.
Thank you.
Bye-bye until 1:30 p.m.